Here we'll talk about kinetic energy, but we'll review gravitational potential energy a little bit before we start. A ball is dropped from the top of a tall building. Which of the following would describe the ball's gravitational potential energy time graph? Well, gravitational potential energy depends on the object's mass and its height. In this case, the object's mass is not going to change. But we know that its height will. As it falls from the top of the building, its height will decrease a little bit in the first second, and a little bit more in the second second, and then a little bit more than that in the third second, because the object's speeding up as it falls. We know that gravitational potential energy is equal to mass times g times h. Since mass isn't changing and g isn't changing, we know that the gravitational potential energy will also decrease with a graph that looks like this, where the graph gets a steeper negative slope over time. And so that means that the gravitational potential energy time graph is decreasing at an increasing rate. Kinetic energy. Here's the cheetah. The cheetah's got lots of kinetic energy when it's running, because objects with speed or objects that are moving have kinetic energy. All objects in motion have kinetic energy, in fact. Now recall from Newton's second law that when we have a force that's applied to an accelerated object from a speed v1 to v2, the work done on the object can be written like this. And this is our work done right here. So we've seen that formula before. And we know that net force is equal to mass times acceleration, so we can rewrite that as work is equal to mass times acceleration times delta d. Using our kinematics equations, we know that acceleration is equal to v2 minus v1 over delta t, and we know that displacement is equal to 1/2 times v2 plus v1 all times delta t. So those are two of our 5 equations of motion from kinematics. So we can substitute those expressions in for mass, acceleration, and delta d. Our mass, of course, remains where it is, but we have our acceleration here and our displacement here. So that gives us 1/2 m times v2 squared minus v1 squared when we do some algebra there. So the work in this case is done to change the speed of the object, in this case to increase the speed of the object. The energy that is increased is the object's kinetic energy. So the work is equal to the final kinetic energy, which looks like this, minus the initial kinetic energy, which looks like that. So the work is equal to the change in kinetic energy. That tells us that the kinetic energy at any instant is 1/2 times m times v squared. We should keep in mind that the mass should be in kilograms and the speed v should be in meters per second, because we want to get joules for our units for kinetic energy. Here's an example. We have a car with a mass of 1,500 kilograms. It's moving at a speed of 24 meters per second. Let's calculate the kinetic energy of the car. So here's our mass, our speed, 24 meters per second. Our unknown, so those are our given values. Our unknown is EK, kinetic energy. So we'll select our equation, which is our new equation for kinetic energy, and then we'll substitute the values that we know and we will solve. So here we get 4.3 times 10 to the 5 joules. Let's try another one. An object of mass 5 kilograms is traveling at a speed of 4 meters per second. 27 joules of work is done to increase the speed of the object. Calculate the final speed here. Again, here are our given values. Here's our unknown value. Our work equation, and this is often referred to as the work energy theorem. So this is our work energy theorem, which tells us that the work that's done on the object is equal to the change in the object's energy. In this case, it's the change in kinetic energy. However, later we'll see that we can use the work energy theorem with other kinds of energy. We could do work on an object to increase its gravitational potential energy or to increase its elastic potential energy, but again, we'll look at those later. We want to solve for V2, so we rearrange the equation to get V2 by itself, and it looks something like this. And so now we can substitute the values in that we are given in the problem. And we get 5.2 meters per second. All right, now we're going to try an activity, an inquiry activity, to see if you can measure your own kinetic energy. And here we'll try a few practice questions as well.